All right. So there's essentially 3 pump laws, and I want to look at identifying each one of these things. So the first pump law that we deal with is up on the top, okay, right there. That particular pump law is one that essentially identifies its RPM and the flow rate are kind of they go directly proportional. They're kind of 1-to-1 ratio is how they function. So if I change the RPM of a pump, I expect a proportional change in the GPM of that system. So if I slow a pump down, I expect a proportional change in that as well. So that's simply what that is. Very much like a fan law. The only thing is we've just changed the medium. Pump law number 2 is a very commonly used pump law, and that one identifies where the pressure drop that you get in the system, whether new is a resulting change of the square of the flow rate change or the RPM change. So in other words, that this particular system that we're looking at here is showing the pressure, which is going to be this pressure right here, will typically either be in feet of head or it will be in PSI. Either one of them will work as long as you are using, it has to be the pressure drop or it has to be a delta P. It can't be just a single pressure. So that's a fact. So when we look at the second pump law, that particular one is it's just rewritten around a little bit to solve it, very much like I was just calculating in a previous YouTube video. So this new pump loss, new pressure drop of the system is determined by taking the new GPM that you desire over the old GPM, and you're going to square that. And when you square that, you're going to take that times the old pressure drop of what you had at the GPM of the old, and you're going to find that that's going to give you what your new is. And that's a very useful formula. We use it a lot in our applications. So, and of course, the last one of the pump laws is pump law 3. And that one identifies that as you change the GPM or the RPM, that the horsepower will change, but it doesn't just change a little, it changes by the cube of that change. So it's huge that the amount of reduction in horsepower that will happen with fairly small changes in GPM. So it's to our advantage to try to understand that. That's the whole basis of why we use frequency drives in systems. In your commercial applications, you can save customers a significant amount of money if you really understand that. So this pump calculation, to some extent here, it talks a little bit about how much energy is a pump going to need to operate when I look at the pump efficiency and what's the formula. So I'll just go through a quick little example. If I happen to have a system, for example, that was going to run 10 GPM, and I was going to work that against, let's say, 5 feet of head, as an example, and I was using water, and water has a specific gravity of 1.0, so it's 1.0 specific gravity. And I'll put that over a constant of 3960. And I'll take that times the pump efficiency. So let's say that pump efficiency happens to be 50%. So I'll put on this thing as 0.5 as the efficiency on this one. So now if we look at the calculation here, we'll see what that does. So we've got okay, and we're going to run 10 times 5 is 50, and of course 50 times 1 is 50. We're going to divide that by So we'll find that to do that work, we really only need 0.025 horsepower, or brake horsepower, we'll say. Very, very tiny amount that we will need to do that kind of work. So it's in a larger system, it would be more appropriate to be doing that. In the small systems, we don't really worry a whole lot about it, just because it's too minimal, too small. So this next calculation is primarily how much energy am I adding into the water in what they call water horsepower. And what you're going to notice that is not happening here is there is no pump efficiency in this particular one. So really the difference between water horsepower and brake horsepower is the water horsepower is really only what the water sees, and the brake horsepower is what is it going to take to do that water horsepower, to add that water horsepower. So let's look at another example here. So in this case, I described to you a little bit on how do we do this. So the energy that I'm adding to this water is that mechanical energy. We're transferring it to the water. So it does take into consideration, it does not take into consideration the mechanical efficiencies of the pump or inefficiencies of the pump. So all the pumps are going to have some inefficiencies, and they're not going to be, in fact, they're, I would say, quite inefficient in many cases. So in this example, I'll use a 25 GPM system against 15 feet ahead, and we want to know what is the water horsepower. What are we adding? So 25 times 15 times 1 divided by 3960, and you'll notice that it only takes 0.0946 water horsepower. So that's really what the water is actually seeing for energy added. So now let's add some energy due to the drive losses of the pump itself. Just the pump, the inefficiency of the impeller, the housing, what does it take to add that energy of the water horsepower? So let's take a look at this same example. So 25, 15, and what we're going to do is use water, and water has a specific gravity of 1, but this pump is only 40% efficient. So what is the brake horsepower? So when we look at this example, you'll notice that the amount of energy needed in this example comes out to 0.2356 brake horsepower. So it's a very tiny amount. This formula will work almost to the T. If you were to look at every single manufacturer's pump curve, and as long as you know what their efficiency is, you can figure out exactly what that brake horsepower is. What kind of a horsepower demand is it going to take to do this work? It is spot on the money. All right. So let's look at an example of pump law number 1. So pump law number 1, what we're going to do is this. We're going to take a system, and again, I'm going to reiterate this. This is a directly proportional speed of the pump to flow rate. And so let's take a look at this. We've got 25 gallons a minute. We're going to do this against 1750 RPM. The system is only going to require 20 gallons a minute, or if the system only requires 20 gallons a minute, well, what can I drop the pump speed down to do this? So in this case, I'm going to set that equation up proportionally with the 20 being my new GPM. My 25 is going to be my original or old GPM. And remember, the 25 has to directly correlate to the 1750 RPM because that's where the two are tied together. Now, when you do the math on this thing, it's going to identify that your new pump speed could be dropped down to 1400 RPM, which will yield you the 20 gallons a minute. Now, of course, the advantage of that is it's going to pull less horsepower, it's going to pull less amperage. All those things are going to be advantageous. All right. So the way we would do that is obviously with some sort of a frequency drive in the field. So, and that's just one example. So what do you say we take a look at the second pump law? Now the second pump law is going to be what we're going to use to identify what is the resistance going to be when we have the original flow rate that we were dealing with of let's say 20 GPM or 25 gallons a minute. And if I drop it down to 20, what is it going to do? What's going to happen to this? So in this case 25 GPM. We're going to run 1750 RPM. We're going to do this against 20 GPM, and the original resistance is 10 feet ahead. Now that 10 feet ahead correlates to the 25 GPM. So let's find out what the resistance will end up being. So when we plug it in my formula, I've got 20 divided by 25, and I'm going to take that whole quantity squared times 10, which will yield me down to 6.4 feet ahead. Now 6.4 feet ahead, that is the new resistance that we're going to end up getting. 6.4 feet ahead is my new resistance that I will have against, just going against the 20 GPM. So what's interesting about this is we saw about a 36% reduction in feet ahead with only dropping down 5 gallons a minute. So that's a fairly substantial amount. So let's take a look at the next thing. So in this example here, I just wanted to shoot this out here as an example on here. And in this one here, I'm just showing a system. I've got it designed for 8 gallons a minute of flow. It's against resistance at 10 feet ahead. One thing I do like about this particular pump graph that I have with all these pump curves on is the system curve. It's got many lines already drawn on it, which makes it a lot easier for me to do this. So it's really, really nice on this one. So in the example that I could use on here, if let's say I said, well, I want to design my system for 8 gallons a minute against 10 feet ahead, and I want to know, well, is this a good pump, or do I need to do something? Do I need to do any calculation on this? That's really where that second pump law really comes in handy. And in this example here, if I happen if I look at this one here, as you can tell, at my 8 GPM, and it's going against just over 10, it's incredible how close that is. Now in real life, you would say, well, that's totally good. I could choose pump 5 or pump 7. Either one of those would be perfect. So pump 5 is the 1542F brute pump. And of course, pump 7 is the UPS, which is anytime you see UPS on the Grundfos pump, that tells you it's a 3-speed or a multi-speed pump. So a 1542 speed 3 pump. Either one of those two would be so really good, and no issues there. But that's an easy one. Now, if the original point was 10 GPM at 12, now we'd have to calculate some other points because, well, what do I want to do? How am I going to know where we're going to really run? And then, of course, I have to plot those curves or those points at the other things, just like we did earlier. And, of course, that would tell us exactly where that ends up system will end up being. So I've already done some of the calculation here already, where I took the 12 or 10 GPM at the 12 and I plotted on the curve, on the chart. Now you'll notice it didn't land on any points. I'm already right here. So we just need to plot the system curve and figure out where things are going to run at. So I picked several different points. So I ended up picking 8 GPM, and I'm just picking these out of thin air. I'm just trying to figure out where am I going to run at. Now, ultimately, in real life, what you'd really want to be doing, guys, is you probably want to pick points that are maybe going to end up close to your curve that you feel you're going to run at, and then you just keep picking more points that are going to get you close. And if you're lucky enough where you have the electronic devices with a pump curve, with the pump curves on your phone or on your iPad, you can essentially just tell it, hey, this is what the resistance is, where's it going to run at? And it'll figure all of this out for you. So I picked out essentially 8 GPM and comparing that to the 10, and I squared times 12, it comes up to 7.68. I picked 5 at 10, and of course that 12 now became 3. And then of course I picked 12 over the 10, and that comes up to 17.28, and then the last one is 14, and the 23.52 was the calculation that it came out to. So what does that look like? So when I punched this out on the iPad as I was doing this, on the computer as I was doing this, I figured out that my actual point of operation would be right here at this circled point for pump 7. wherever that star is on there. And I thought, well, that's interesting. So at a pump curve 7, I figured I would get roughly about 9.2 gallons a minute against a resistance of about 9.8 feet ahead. And that's generally how you're going to want to do those things to figure that out. Now, what if I would have picked, if I said, well, I want to I'm going to use pump curve 10, the 4364 FC, this pump curve 10. And of course, that's this one. And of course, that point of operation, you can see there's about 3 curves that are all intersecting at the same point. But whether you chose 10 or 4, you would have had exactly the same amount of flow rate, GPM, the whole thing would have been identical. And of course, that would have given you more flow, but it would have given you roughly in the probably, maybe 11.7 GPM, but you would have been working against roughly 17.5 feet ahead is what you'd have been running on there. So again, if you don't need that flow, there's no reason to buy that more expensive pump if you can get away with the lower one. And it makes way more sense. You're so close to the original design operating point. With this other one, it makes sense let's just use that one. I think that's really where I want to run at. But that's super, it's such a good skill to know how to do. Let's take a look at this next one. So the next curve, I wanted to pick a commercial pump curve and to show you what kind of goes on in this thing. So on a commercial curve, you're going to notice that we're going to have a certain amount of flow rate and GPM that you're going to run. You're going to have, just like the other residential curves that we looked at, you're going to have all these different impeller sizes. So you'll notice that the impeller diameters, they range anywhere from 8.05 inches all the way up to 10.4 inches. Your pump net positive suction head that's required is anywhere from 3 to 15 feet ahead. Now that is something that I haven't necessarily talked about yet, and that's something that we'll have to deal with specifically. It relates to the amount of pressure that must be going into a pump. Otherwise, you'll get water to start to cause it to evaporate and create and go into vaporous standpoint. So we have to really, as long as we keep our pressures up, we should be in pretty good shape. We have all of our pump efficiencies, and you'll notice that the pump efficiencies are in a curvature manner. And as you can tell, we're going to run anywhere from about a 30 to about a 48% efficiency. And then, of course, these are also fairly important, the brake horsepower lines. And you'll notice that that's just giving us a rough idea so we know what size motor to pick. So that's typically the way we would be doing this. So very, very basic, very similar types of systems. Every manufacturer has all of these different pump curves commercially that are out there, and so it's a fairly simple. The only difference is now within that same one pump that you buy, this model 1510, you now could have up to 1, 2, 3, 4, 5, 6 different impeller sizes within that one pump. So you'd have to know what impeller did they put in there. And oftentimes they will note that or stamp it or mark it so they know what's in that pump. Otherwise, you really don't know. You can also tell that the efficiency range of my pump is much better in that middle third to some extent. So if we wipe this out and we wipe this out, you'll notice the middle third is really my sweet spot on there. So in this example, I wanted to do a quick example with you commercially where I'm going to take a system designed for 40 gallons a minute of flow at a resistance of 20 feet ahead. And my system fluid is water, and then I need to pick some more of those points. So just like I did earlier, and I thought, let's just pick some points, and I picked 44, 20, 48, 54, and 60, and I figured all those resistances that are shown in there. And then what I did was I drew those out. I marked those points, and I just kind of drew my curve out as best I could. And it's essentially what it allows me to do is to determine what is going to happen, and what am I going to run if I end up getting these, if I choose to have that. So if I end up using the 8.05 inch curve, I'll end up getting 44 gallons a minute against 24.2 feet ahead. But it's only going to be about 37.5 or 37% efficient. Not very good. Not that this is a very efficient pump to begin with. So now if I say, I want to go to a bigger impeller. I want to use a 9-inch impeller. And the 9-inch impeller, if I bump it up to the next spot, that 9-inch impeller, we're going to find my point of operation will be much, much closer to 50 GPM at about 31.2 feet ahead. And the efficiency of the pump is actually getting better. It's up to 41% now, and a whopping 4%, and it's going to require approximately about 0.85 brake horsepower is what we'll end up running on there. So we, like I said, we may not necessarily need that, but you can always adjust it one way or the other, or maybe there's a balancing valve. Typically, you want to try to pick maybe pumps that are going to give you maybe a little bit of extra pump, just in the event that extra flow rate in the event that there's a mistake made. And no matter how good you design a system and install it, it never works out exactly the way you anticipate, not to the T. It's just, you can get close, but you never expect perfection on this. All right, so another point that I wanted to make on this one is I wanted to calculate the water horsepower of what we're adding, and I thought I would choose a system that is requiring 47 GPM against 28 feet ahead. And in this case, we're going to use water, and that would require a 0.332 horsepower. Now, if we take a look at the efficiency of this pump at that flow rate and head, that would be 40%. So when we take a look at that, you'll notice that it comes out to 0.83 brake horsepower at that 47 GPM. So that's pretty much spot on with where the pump curve is telling us that it is. So this is just a numerical way to calculate what the brake horsepower needed is. This is something that the part of the reason why you maybe concern yourself with this to some extent is if you have a point of operation and you have a pump that is maybe over amping, and you're trying to figure out, well, is it maybe they have too small of a motor on here, what it might be. It's a way for you to kind of double check things to see, is there something that they did to this that would have caused this? So, for example, they could have had a 1-horse motor on it, but they have a demand for 1.25 horse of brake horsepower. So that's part of the reason for doing some of this. So